Welcome back to the online tutor. Today I am going to describe the complex numbers. What is a complex number? That's the important thing. Before that I will describe about the number set. In our O level, we have a number set which is called real numbers. Real number. Inside the real number, we have rational numbers. Again, rational numbers derive into integers. Integers again derive into positive integers. Okay. And also, real number, positive integer is a subset of integers. The integer is a subset of rational number. The rational number is a subset of real number. In between rational numbers and the real number, we have another number set which is called Q dash, irrational numbers. Right. So this is the largest number set that we have learned in grade level. But over there, we have another number set which is called complex numbers. Right. Actually, a real number is a subset of the complex number. Over here, the complex number is the largest number set that we have. Complex numbers. Okay, the next important thing is why we are using complex numbers. The answer is given in this example. So this is a quadratic equation. So normally if it is equal to 0, then we are going to find the factors. So the 7, I'm going to factorize using computing square. Plus 1 and plus 7 plus 1 is minus 1 equals 0. X plus 1, 6 equals 0. X plus 1 square equal to minus 6. Right. We are in trouble. We can't use a square root for the negative numbers. X plus 1 square minus 6. We never use these kind of situations. The square root inside the negative number. But you all have learned about discriminant. What happens when the discriminant is less than 0? We mean 2 square minus 4 into 1 into c is 7. 4 minus 28, you can see it's negative 24. Discriminant is less than 0. In quadratic equations, we have learned this kind of situation. So over here, we always wrote the roots are non-real. So the roots are non-real means the roots are surely complex. That is the main important thing about complex numbers. All the quadratic equation, there should be a root. We can't say that quadratic equation doesn't have root or something like that. Always the quadratic function should have 2 roots. In this example, all roots are non-real. Non-real means the roots are complex. Okay, let's look at the definition of the complex number. The definition of the complex number is x plus iy. Here xy are real numbers, but I is an imaginary part. Actually, in a complex number is a x plus iy. We have 2 parts. This part is known as real part. This part is known as imaginary part. actually I is the representative of the imaginary. I into y is the imaginary part. If a complex number x is 0, that known as z equals 0 plus iy, these kind of complex numbers are known as purely imaginary complex numbers. If y equals 0, if x equals 0, if y equals 0, these kind of situations we call purely real parts, purely real, as it's like a real number. So all the real numbers, their complex part, their imaginary part is 0. Okay, what is this I? Actually, I is square root minus 1. I is square root minus 1. When you are squaring I, then I squared will be minus 1. This is the only number that we have when we are squaring a number which gives negative value. So most of the time when we are squaring a number which gives positive answer, but only for the I, when you are squaring I gives the same negative value. This is the only number that we have used the square as a negative number. But I to the power of 4, it's I square to the power 2, no? Minus 1 to the power 2, which gives positive answer. I to the power 3, I to the power 3 means I into I square. I is square root, I square is minus 1, then it is minus I. Let's look at I to the power 2020. What's happened? I to the power 2 to the power 1010. So I to the power 2 means minus 1. Minus 1 to the power even power, it's plus 1. But I to the power 2019 or something like that. 2019 means I to the power 1 into I to the power 2018. I to the power 2018 means 2 to the power 009. Here I to the power 2 means minus 1, but minus 1 to the power odd number is negative. When minus I, the answer is minus I. These are the simplifications of the I. So actually I is known as imaginary part. The definition of I is square root minus 1. I have to memorize these two. Now you can try I to the power 27, I to the power 1024, right? You can try these. I to the power 2025, right? Try yourself. Okay, let's look at the basic operations of the complex numbers. Basic operations in two complex numbers. Assume Z1 is a complex number which is x1 plus iy1. Z2 is another complex number x2 plus iy2. As the first one, I am just considering the addition of these two, z1 plus z2, x1 plus iy1, x2 plus iy2. Here these are real parts, we can separate it. The other are y1 plus y2, it's the imaginary part. So addition of these x1 and x2, it's another number, x. y1 plus y2, it's another number. So you know x1, x2, y1, y2 all are real numbers. The I is the only imaginary part. Others are real numbers. y1 plus y2, which is y, iy. Here z1 plus z2, it's again gives another another complex number. So it means if you are adding two complex numbers, the answer is another complex number. What about the subtraction format of the two complex numbers? If you're subtracting two complex numbers, z1 minus z2, here is minus I. It's x1, so the bracket it's minus x2 and plus I y1 minus y2, and here x1 minus x2 is another real number, y1 minus y2 is another real number. So it means when you are subtracting two complex numbers, which gives another complex number. Right, let's look at the product of the two complex numbers. z1 into z2, x1 plus y1, x2 plus y2, x1 x2 plus I x1 y2, y1 x2 plus I squared y1 y2. Actually I squared mean minus 1, no? And you can connect these two, x1 x2 minus y1 y2, because this is minus 1, this I is minus 1. Plus here I can be taken out, x1 y2 y1 x2. Right, you can see it's again like a complex number. So real part x plus I is an imaginary part. Therefore the product of the two complex number is another complex number. The product of two complex number is another complex number. Okay, let's look at the division of two complex numbers. z1 over z2, x1 iy1 x2 plus iy2. Over here I'm going to multiply by the conjugate of the denominator, x2 minus iy2, x2 minus iy2. I'm just multiplying by their own conjugate. So the numerator, which is x1 x2 minus I x1 y2 plus I y1 x2 minus I squared y1 y2. What about denominator? You can see the denominator is one is another conjugate. Conjugate means this is the factors of the difference between two square. x1 x2 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 is x2 square minus I squared y2 square. So actually I square means minus 1. The minus 1 into minus 1, minus is plus. Here also minus into this minus, this I square. So all I squares are minus 1, all I squared are minus 1. Minus into minus is plus, minus into minus is plus. Then x1 x2 here is plus, x1 x2 plus y1 y2 plus I here y1 x2 minus x1 y2. On the denominator, which is x2 square plus, because square is minus 1, minus y2 square. Right. So I'm going to divide by individual. divide the denominator by individually, then it's like z1 over z2, which is x1 x2 y1 y2 x2 square y2 square plus I x2 square y2 square, here y1 x2 minus x1 y2. So what is this? This is another real number because it has x, y, only xy. Here also the real number. So I'm z1 over z2. This whole thing I'm presenting as one single capital X. This whole thing is assumed as one single capital Y. X, Y are real numbers. Therefore, final interpretation, the division of two complex number is another complex number. Okay, up to now we have learned what is a complex number and why we are using complex number and the basic operations of two complex numbers. We had four operations: plus, minus, and product, and the addition, subtraction, multiplication and division. We discussed those operations. Right, now let's discuss some examples. Example number 1. Find the real part and imaginary part of the following. First from now, I'm 3 minus 2y, 4 plus 3y. Right. Can multiply these two. 12 plus 9 minus 8i minus 6i square. I square means minus 1. This is plus 6. 12 plus 6 plus I. This is 18 plus I. So the real part, I'm taking this as Z. Real Z is plus 18. Imaginary Z, which is plus 1. Here the coefficient is plus 1. Okay, as a second example, taking 3 minus 2y, something like that. So here you can see the denominator is irrational because I mean square root. So once square root is on the denominator, the whole thing is irrational. So we have to multiply it by their own conjugate. 3 plus 2y. Then it's 3 plus 2y. 3, this is the factors of difference between 2 square. 3 means 9 minus 4i square. 4i square, I square means minus 1. Minus 1 into minus 4 is minus 8. So it's 3 plus 2y over minus plus 4, it's 13. So it's 3 over 13 plus I into 2 over 13. So this is the real part. This is the real Z. This is the imaginary Z. Imaginary Z. Okay, let's look at another example from number 3. 3 plus 2i, 3 minus 2i, 4 plus 3i. So over here the same thing, we have to multiply by their conjugate. 4 minus 3i. Here it's 12 minus 9i square, minus 9i and minus 8i plus 6i square divided by conjugate. It's 16 minus 9i square. I squared means minus 1. 12 minus 6 is 6. Minus 9 minus 8 is minus 17. Minus 17i. Divided by I squared means minus 1. Minus plus 9. 16 plus 9. It's 25. So it's 6 over 25 plus I minus 17 over 25. So you can see this is the real part. This is the real Z. This is imaginary Z. Imaginary Z. So now I think you might have some idea about these kind of examples. What we have done, we always rationalize the denominator. Okay, let's look at special identification of this. 1 plus I to the power 2. What is this? You can expand 1, the product of terms and multiplied by 2, and I square. We know I square means minus 1. The minus 1 and plus 1 getting cancelled. It's only 2y. So that means 1 plus I to the power 2, it's 2y. If someone asks 1 plus I to the power 4, then you can write it's 2y to the power 2. So it's 4i square. I square means minus 1. It's minus 4. 1 minus I to the power 2. What's happened? Here it's plus 1. The product is minus 2y and plus I square. These two again cancel. It's minus 2y. So 1 minus I to the power 2, it's minus 2y. Third one. Minus 1 plus I to the power 2. Minus 1 is plus 1. The product is minus 2y. And the last one is I square. These two again getting cancelled. And it's minus 2y. The last one. Minus 1 minus I square. Minus 1 is plus 1. The product is again plus 2y. The last one is I square. So I square and these two getting cancelled, plus 2y. So you can see it's 2y, it's minus 2y and again plus 2y. This is another special identification of a complex number. Okay, let's look at another example. This is taken from 2001 LL paper. Express 5 minus I over 2 minus 3i as lambda into 1 plus I. Find lambda. Okay, I think we have done these kind of questions. What we have done, we multiply by their own conjugate plus 3i, and it's 10 plus 15i minus 2i and minus 3i square over 4 minus 6i square. So here it's 3i square mean plus 3, it's 13. And here it's 39. Actually 13 can be taken out. 1 plus I. The denominator, it's I square mean minus 1. Minus into minus is plus 1. Plus 6 plus 4, it's plus 10. Okay, now you can see lambda is 13 over 10. Lambda is 13 over 10. What of the next part? It's 6, it's 4, 3, 3, it's 9. Sorry, here it's 9. It's 9 and 13. 13 over 13 is 1. So lambda is 1. This is also 30. These two getting cancelled. And lambda is directly 1. Sorry. Show that 5 minus I to the over 3 minus 2i whole thing to the power 6 is a purely imaginary number. So can you remember in the theory part I told you if the real part is getting 0, this complex number is known as purely imaginary number. If the imaginary part is getting 0, that number is known as a purely real number. Now they asked to show this number is purely imaginary number. So before that you have to simplify it. Now we have simplified this part. It's like 1 into 1 into 1 plus I, it's to the power 6, right? So can you remember 1 plus I to the power 2, again to the power 3, 1 plus I to the power 2, it's 2i, 2i to the power 3, it's 8, 8i, I cube mean I into I square, I into I square. I square mean minus 1 minus 8i. Minus 8i. Right. It's true. It's minus 8i. Minus 8i mean the real part is 0. We have only imaginary part which is minus 8. Then you can interpret the answer. This number is a purely imaginary number because the real part is getting 0. It's only minus 8i. Okay, now you can do it as a homework. Find the real z and the imaginary z of that z. You have to simplify it. Okay. Now let me consider another theory part. The first theory, the condition of a complex number to be 0. If z is a complex number, x plus iy should be 0. 0 means the real part x z equal x plus iy. If this complex number is a 0, 0 means the real number, the real part and the imaginary part, the both should be 0. It's like 0 plus I0. So the real z is getting 0, imaginary z should be getting 0. Separately, both should be getting 0. What is the condition of two complex numbers to equal? Assume z1 as x plus iy1, z2 as x2 plus iy2. If these two are getting equal, z1 equal z2, which means x1 plus i1 equal x2 plus iy2. You can see here x1 plus iy1 equal x2 plus iy2. So which means both real part and the imaginary part are equal. So x1 should be x2, y1 should be y2. The imaginary part of the z1, the real part of the z1 should be equal to the real part of the z2. Imaginary part of the z1 equal imaginary part of the z2. That is the condition to be satisfied. The imaginary part and the real part should be separately equal.